what happens when a current carrying coil is placed in a magnetic field. So far we have done that if a charge Q moves in a magnetic field, this is the force that acts onto it. If I place a wire with current, this is the force that acts onto that current carrying wire. Now this time it's a current carrying wire only, but taken in the form of a loop. I have taken a loop P, Q, RS and placed in the magnetic field in such a way that perpendicular to the plane makes an angle theta with the field direction. Okay, so this is the area vector perpendicular to the plane, and this is the direction of the magnetic field. So it is kept like this. You can see from here. If I see from the top, it appears like this. So this is area vector. This is, so now this angle is 90 minus theta, this is theta. Okay, so this angle is 90 minus theta and this one I have taken theta. The purpose of taking the angle between the area vector and the magnetic field, I am taking the angle between magnetic moment and the field. This is required actually, right? You can take the other angle also as 90 minus theta, but then later on you will have to change it. So this angle, the plane is at an angle 90 minus theta with the field direction. Okay. We know that each side will experience a force ILB sin theta. Now let us find out the force on each side and see what happens. So force on, let me start with this PQ. It is I L B sin 90, which is ILB. See this side, again, when the magnetic field is in this direction, this is the coil, so this side is always perpendicular to this, and same way this side is also perpendicular. It is only this and this of which the angle will change with the field if I change the orientation. Otherwise this and this, they are always perpendicular to this, right? But this will change. If it is like this, the angle between this and magnetic field is 90. If I keep it like this, area vector, magnetic field, area vector, magnetic field, that angle is 0. Area vector and magnetic field 0. Plane is perpendicular to the field. In this case, plane parallel to the field, area vector perpendicular to the field. Okay. What is the direction of it? We can apply Fleming's left hand rule or right hand cross product rule. The current is in upward direction. Current is this. This is the direction. And this is the magnetic field. This is IL. So L cross B inward. So this side experiences force in one direction. Or I can apply Fleming's left hand rule too. This is forefinger, field, central finger, current, up, field this, so force is upward, inward, sorry. Same way on RS. It is I, L, B, sin 90, I, L, B. So this is inward, inward means perpendicular to the plane of the board. And on RS, central finger, this in the direction of current, forefinger in the direction of the field, so field is outward. So this is out. Or this time this is IL, field outward. Right hand rule. This says that if we turn our fingers from first vector to second through the smaller angle, thumb should give the direction. So in this case, L, B and here L, B. cross product rule. Okay, now QR. QR. If I am looking from the top, this is the direction of current, QR, and this is the magnetic field, and this angle is 90 minus theta. If I am looking from the top, right? So this is like this, area vector, field, this angle, and this is the area vector, this is the magnetic field. This angle is theta, and this angle is 90 minus theta. We have already done 90 minus theta. How much force will it experience? I, B sine 90 minus theta. And what will be the direction of it? B to B, down. Now see here, B is this and this B is this. Length this side, B. So it will be upward. See all these directions very carefully. Upward. On SP, I, B sine. Now what will be the angle? Now this is the direction. This is S, this is P, so this is the angle. 180 minus 90 minus theta. Okay, so it becomes 90 plus theta actually, and is downward. Again, they are also equal. Sin 90 minus theta, sin 90 plus theta, both are cos theta. Okay. So this is a coil, and I have marked all the forces. So now again, see, this is the coil. This side experiences upward force, this side downward force. They are equal and opposite. They will cancel out. This side experiences force inward, this side experiences force outward. Now if I pull this out and push this in, what will happen? This will rotate. So these two forces will constitute a torque. These two forces. The reason being, these are, if I ask what is the net force, it is 0. This is equal and opposite to it, this is equal and opposite to it. But even then, these two forces will constitute a torque because these forces are not acting along the same line. So they will not cancel out. Net force will be 0, but they will constitute a torque. So if I look from the top, it will be easier to work out if I am doing that way. Q and R, this angle is 90 minus theta, and this side is being pushed in and this being pushed out. Now let me work out what is the torque. One force acting along this line, one force acting along this line. I need actually this distance. How much is this force? ILB. Each side will experience ILB. This ILB in, this ILB out. Now what is, these two forces cancel out. So ILB in, ILB out. And what is the perpendicular distance between the lines of action? One force acting in, one force acting out. So again, see it here. This is experiencing force in, this is out, like this. If I see from here, this is experiencing force out, this is in. So I need this distance. I need this distance. This is B. This is 90 minus theta, this is 90 minus theta, this is B, so it becomes B. Okay, let me work out this distance. This is 90 minus theta, so this will be 90 minus theta. Okay, so this will be theta. So B cos theta, and this will be B sin theta. The torque that will act on this coil. So NIAB sin theta A is the area of the loop, L into B. Now, this term, I into A, if you can recall, this we call as the dipole moment. So this can be written as PB sine theta, or in vector form I can write it P cross B. So whenever a current carrying coil is placed in the magnetic field, it experiences a torque. We can compare this with the result of the behavior of electric dipole in an electric field. If you can recall that plus charge, minus charge, electric dipole at an angle theta, the torque is PE sine theta. Then we derived an expression for its potential energy also and found the two positions, one for stable equilibrium, another for unstable equilibrium. Plus here, minus here. This is the direction of dipole moment, theta 0, so torque is 0 and U is minus PE. Stable equilibrium. Equilibrium means torque is 0. But if U is minimum, we call it stable equilibrium. If U is maximum, unstable equilibrium. Actually, the criteria is if we displace a body, if I keep it like this, net force 0. But if I displace it, it will fall down like this. But if I keep it like this, I displace, it comes back. So this is a stable equilibrium and this will be unstable equilibrium. Same way here. If we displace the dipole, it returns stable equilibrium. But if minus is here, plus is here, even now theta is, torque is 0, but U is plus PE. This is unstable. If I displace it, it will topple. Now, for magnetic dipole, the coil that we have done, torque is NIAB sine theta or PB sine theta. This is the torque that is acting. Theta 0 means P and B are in same direction. How we find the direction of P? Right hand curve rule. If we turn our fingers, keeping in the direction of current, thumb gives the direction of dipole moment. So from this side, okay, if this is the coil, current is flowing like this. So P will be like this. Okay. So the plane is perpendicular. This is the situation and the current is coming like this. So if the current is coming like this, dipole moment is in this direction. So theta is 0. So torque is 0. U is minus PV. Stable equilibrium. For unstable equilibrium, plane still needs to be perpendicular. The only difference is that this time the direction of current should be opposite. Sorry. Direction of current will be such that the dipole moment is in this direction. When is it possible? Dipole moment in this direction. So the current should be like this. Current is like this. So dipole moment here, B is here, theta is 180, torque is 0 and U is plus PB. Unstable equilibrium, stable equilibrium. So a coil placed in a magnetic field experiences a torque, the magnitude of which depends on the orientation of the coil. Torque is PB sine theta. So that's enough. This is actually the principle of galvanometer, ammeter as well as voltmeter. So do it carefully, it will be followed by moving coil galvanometer. Thank you.